So let's start with Kepler's laws. Let's start with Kepler's laws. And there are three Kepler's laws. The first law says that the orbit of a planet is an ellipse with the sun at one of the two foci. So you might essentially, the picture is somewhat like this. One sec. Yeah, the picture is kind of like this. Here's an ellipse, here's the sun, and here's a planet, right? And the sun is located at one of the focus of an ellipse. So if you're familiar with what an ellipse is, you will know what I mean by focus. And the second statement says that a line segment joining the planet and the sun sweeps out equal areas in equal intervals of time. So which means essentially something like the, if I say this angle is theta, the time required to cover this particular area is constant. So this means essentially this means that the aerial velocity of a planet is constant. So if I say this is theta 1, let's say, and you have some other angle, let's say theta 2, then, and if I have let's say theta 1 equal to theta 2, then the time required to cover both of these areas is constant. Or you might consider that the velocity of the aerial velocity in going from this starting point to theta 1, and the aerial velocity in going from starting point to theta 2 is constant. And the third law says that the square of a planet's orbital period is proportional to the cube of the length of the semi-major axis of its orbit. So again, if you're familiar with an ellipse, you should know what the semi-major axis is. But and the orbital period is referred to, by the orbital period we mean that the time taken for a planet to complete one rotation. So what's important is that the first law and the second law were both published by Kepler in 1609, while the third law was published in 1619. And the primary motivation for Kepler in order to do this was that he recognized that the prevalent theory, which was actually not accepted by the church, of course, but the prevalent theory during that time was that orbits are circular, which was actually mentioned by Copernicus. And Kepler found that this could not explain Tycho Brahe's observations. So Tycho Brahe is a Greek astronomer, was a Greek astronomer, and it could not explain Tycho Brahe's observations on the orbit of Mars because Mars has, amongst the inner planets, Mars has the highest eccentricity of orbit other than Mercury. So Kepler's entire deductions were based on data from Tycho Brahe's observations. The reason the years are important is this. The telescope was discovered in the year 1608. That was the earliest record of a patented telescope. So Kepler could not have had access to a telescope in order to formulate his laws. So it's essentially the entire methodology he had to do was studying data and coming to a conclusion. And it's remarkable that he arrived at laws which approximated the solar system to a very, very good extent. I mean, I don't think like most people who are interested in astronomy, if they were to given a telescope and maybe given a year or so to work out, and even a computer, I don't think it's a very easy problem that to actually experimentally verify Kepler's laws by looking at the orbits of every planet. So it's a remarkable feat that Kepler was able to come up with these three laws without using a lot of mathematical or without using a lot of the current instrumentation that's available. And so let me move on to the Kepler problem. And the Kepler problem essentially talks about describing the motion of two bodies interacting mutually with a force that obeys the inverse square law. And here by a force, we generally mean gravitation, although it's applicable to any inverse square law force. And so we have two bodies. Let's call them M1 and M2, and they are at position vectors x1 and x2. And these interact with the law that is with a force that is proportional to the that is inversely proportional to the square of the distance between them. And if you look at this and you find that, if you look at this and you find out that there's a cube over here in the denominator, you shouldn't worry because uh, this cube is compensated by the fact that you can introduce you can introduce a mod in the above term with and a unit vector in order to remove this cube to a square. So it's essentially an inverse square law. But the problem is this the Kepler's law is a statement about two bodies. It doesn't talk about, it has nothing to do with the fact that there are n number of bodies in the solar system. There is a sun and there are 8 planets, and then as well as there are asteroids and stuff. So the question is, how do we go from Kepler's laws to understanding the solar system? And the general way this is done is using the 1 plus n body problem, where the 1 represents the sun and the n represents the other stuff that's there in the solar system. And then you can write this as a system of differential equations, and we are assuming that capital M0 is the mass of the sun and Mi represents the masses of the other n bodies. And then these are equations that are derived from the previous equation. All of these equations are derived from the previous equation, the fundamental equation describing the motion of two bodies interacting mutually with a force that obeys the inverse square law. And to get a first approximation to the solar system, what we usually do is, if you look at these equations, you can see that these equations hold when each of the masses Mi goes to 0. And the equations hold because you can remove the masses Mi from both sides of the second equation. And then once you remove the masses Mi, you can see that I can let Mj goes to 0 smoothly. You can interpret this in another way. You can interpret this in the way that the entire mass is supposed to be concentrated at the sun or at the mass M0. And if the entire mass is assumed to be concentrated at the sun, then I can also come to the conclusion that the center of mass of the entire system is concentrated at the sun. And you might work this out, that it implies conservation of linear momentum. This is a simple exercise. This is a thought. Yeah.
Before you go forward, what are you doing in the second equation?
Sorry?
First one is like you are taking M0, that is the mass of sun, right?
Yes.
So you are writing Newton's law for mass of sun.
Yeah, so for the first one, you have the Newton's law for the mass of the sun, and for the second equation, you have Newton's law for the masses of the planets. And I might mention that I goes from 1 to n. Right. And so essentially if you place the entire system, the center of mass of the entire system at the sun, what you end up with is that you can show this, that the linear momentum of the system is conserved. And for those who are familiar to a degree with the idea of degrees of freedom of the system, of a given system, if I'm working, let's say, instead of a d-dimensional space in, let's say, 3-dimensional space, then this actually removes 6 degrees of freedom from the space. This removes 6 degrees of freedom from the space. 3 degrees corresponding to placing the center of mass at the coordinate of the sun, and 3 degrees correspond to assuming that the linear momentum is a constant. But then I won't be using this a lot. So this is only for students who are familiar with Hamiltonian mechanics to a certain extent. And then once you do this, you can, so if I assume that the system is placed at x0, that is, it's placed at the coordinate of the sun, you might notice that I can do a origin change of the entire system so that x0 is placed at the origin. And if I put x0 at the origin, then I can basically get rid of the first equation. And for the second equations, I've already mentioned that I'm taking mj goes to 0. So you can write the entire system in this form. And once you write the entire system in this form, what happens is these are a system of n differential equations, but all of these systems are decoupled. So this essentially means that you have n Kepler problems which are non-mutually attracting. So I can essentially study one of these equations. I can take a typical equation from this that is of the form x double dot plus kx by norm of x cube equals 0. And then so this is the fundamental equation that we'll be bothered with. Um, and if you are interested in what is k in case of the gravitational problem, you have k is the gravitational constant times the mass of the sun for the gravitational problem. And you can show that the quantities E and the total energy and the angular momentum are actually conserved quantities. Let me also mention that in this equation, an interpretation of this equation is that you can think of this as a force equation acting on an object of mass 1. So I can actually think of this as this equation, 1x double dot plus k, or let's say gm0 times 1x by x cube is 0. So this is essentially Newton's equation, where the sun is exerting its force on an object of mass 1. And so essentially both the energy terms and the angular momentums can be, or both the terms E and H can be interpreted as total energy and angular momentum. Having said that, let me actually derive one of these. Otherwise, you would be calling me a mathematician if I didn't derive anything for you. So let's derive the first energy equation. So you have this equation, and then what I'm going to do is I'm going to multiply both sides with, I'm going to take the dot product on both sides with x, and then yeah. Oh, I should take it with x dot. And then the first term can be represented as the derivative of half x dot, or half of this dot product. You might be able to see why that is so. And the second term can be represented as this derivative ddt of k by mod x. And again, I'll leave this to you guys to check that this is indeed the case. And so if this term is entirely 0, then I can actually treat this as the constant. So yeah, the total energy is conserved in time, and the total angular momentum is conserved in time as well, which you can actually check by taking the cross product with x on both sides of the equation. Now, the point I want to make is that if the angular momentum is conserved in time, then it is conserved both in terms of magnitude and direction. So what I can actually do is I can rotate my axis, and in case of the conservation of angular momentum, I'm actually working in a three-dimensional space. So I can rotate the x, y, and z axis in such a way that the angular momentum vector is oriented along the z-axis. And so if the angular momentum vector is oriented along the z-axis, I can place my entire problem in the xy plane, because by definition of angular momentum, the position vector is perpendicular to the angular momentum. So if the angular momentum is entirely on the z-axis, then I can place the position vectors in the xy plane. And we'll find that this is important a while later. So as I mentioned, that Copernicus had actually tried to assume that the orbits of the planets are circular. And well, while this is not completely correct, we can actually, so those who are familiar with Hamiltonian mechanics will know that position and momentum are conjugate variables. It turns out that if I consider the locus of velocities in the Kepler problem, then they are circles. So in fact, the velocities in the Kepler problem are actually circles, which are which lie in a plane containing the origin. And not just that, if I prescribe a given circle in a plane containing the origin, I can actually get back an orbit of the Kepler problem. So, um, so let's look at the outline of the proof. So as I mentioned that you can put the position vector in the xy plane, and I can
Actually,
use it. Yeah, yeah,
can you go to the previous slide?
sure, sure, sure.
So, means I cannot follow this theorem. This is about
Yeah, so
you are
this
saying
talks
that
about the this talks about the velocity locus. So given an orbit, how does this velocity move? And it turns out that the velocity moves in a circle, and the circle is in some plane containing the origin. On the other hand, if you prescribe such a circle, so if I assume that there is a circle in a plane containing the origin, then this velocity circle determines the orbit uniquely. Does that make sense?
means you are saying that the orbit is elliptical, but the velocity vector that is circular.
Yes, yes, yes.
And
And as
how
I
do you
mentioned, like
prove this
uh,
thing?
I'll give you an outline of the proof.
Okay.
Okay, and since I am talking about objects of mass one, you can interpret this as a momentum vector actually. Okay,
Okay.
okay. So one thing I'll mention about this theorem that this assumes that the Kepler problem, or this is only for orbits that are non-singular. So, but before I go there, let me just give you an outline of the proof. And so, as I mentioned, that you can place the position vector in the xy plane. So let's use polar coordinates for that. If you put if you assume polar coordinates, then you will find that you can easily derive this fact that r square d theta dt is constant, and this is basically a statement of Kepler's second law. And and then you can use chain rule to figure out that you can use chain rule for using and the Kepler equation, the Newtonian equation, in order to find that the velocity is of this particular form. And but this particular form is essentially the equation of a circle, because you can actually see that it is an equation of a circle with center at C. Because you can see that if I take the norm of this is nothing but k over mod h, right? So so this states that the velocity, so given an orbit, the velocity vector follows a circle, and now I can actually choose coordinates in the xy plane. Also, you might see that this velocity vector is in the xy plane in itself. Now, what I can do is I can choose coordinates in the xy plane so that the center lies on the y-axis. So here you have h, and somewhere on the y-axis you have the center. So on this vector you have over somewhere over here you have h, and over here you have c, and then you have some x-axis over here. And then if you do that, then you can actually use the angular momentum definition to conclude that to conclude that actually r is mod x. Yeah, so you can actually conclude that the norm of x follows something like mod h squared by k times 1 plus epsilon cos theta. Now, this is actually an equation of a conic section with a focus at the origin, and with eccentricity epsilon, where epsilon is defined thusly, and the latest rectum of the conic section is mod h squared by k. Yeah. Now, once we have this, what we could do is uh,
One more thing, actually. I think.
yeah,
Can you
hold on.
elaborate on your second point?
Yeah, which point do you want me to elaborate?
Second point. So you are integrating dv by dt there. Is that
Yeah, 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 yeah.
okay? And how are you
Yeah.
getting the velocity vector? Like v is in the RHS as well as in the LHS, I think. That is v or r.
Sorry,
Uh,
sorry.
uh,
You can find
velocity
dv
vector.
dt.
Yeah,
You
yes.
can find dv day theta from x, right? Actually, sorry. What I mean is you can use dvdt in case of dvdt. You can use the equation that you can use this equation, right? X double dot plus k by norm x cube x is equal to
It's equal to,
0. You substitute. So this x double dot is nothing but dv dt, right?
yeah.
So you plug this in,
Mm-hmm.
and for d theta dt you plug this in, r square by
Log
norm
h
of
by
h by r
x.
square. Yeah, and then
Mm-hmm.
you can from there you have an equation connecting. You have an equation of the form that dv d theta equal to something, and then you can
Okay.
integrate.
Okay.
Yeah,
So we will integrate with respect to theta.
yeah. You're finding v as a function of theta.
Yeah, excuse me. Like I have a small doubt over here. Yeah,
Sure,
so
sure, sure.
instead, like you're basically interested in finding the orbit, like basic in the polar coordinates of the ellipse, right? So instead doing this, like you can try out the method by imparting the Laplace Ranka vector. So the proof would be even more
Yeah,
elementary.
yeah, yeah. No, there are two things I'm doing. For the first thing I'm doing is I'm showing that the velocity is a circle, right?
Yeah. Okay.
Right. And the second thing I'm trying to do, you are quite right that if I use the Rungelin's vector, then it's very elementary and it's a one-liner. The only reason I didn't do it is I didn't want to use a conserved quantity that is kind of non-elementary. That's the only reason I did not do it this way.
All
But
right.
yes, you're absolutely correct. You can use the Laplace Rungelin's vector in order to prove this.
Yeah, because the proof is like this proof is going a bit hectic. So if Laplace Ranka vector
Uh,
can,
well, I had introduced R. Yeah, let me get back. Yeah, sure.
yeah,
You mentioned that no, actually, this proof is not very difficult. If you actually see Milner's original paper on this, the paper is named on the geometry of the Kepler problem.
yeah.
It's quite an elementary proof.
Because I couldn't
I
get the theorem which is in the previous slide, like theorem
okay,
in brackets
I
and
can. So Hamilton's theorem states essentially that corresponding to orbits of the Kepler problem, if you consider the velocity holographs, these are circles,
okay,
right? So if you
yeah,
consider the velocity trajectories,
yeah,
what you end up is that these move in a circle,
all right, okay,
right?
yeah,
So and not just that, if you have a circle, then you can get back to an orbit.
yeah, okay,
You're right.
yeah,
So um, so what you can figure this out from the fact that the angular momentum is position times velocity in order to deduce that r is of this particular form. And once you do that, uh, I'm sorry, it's really r. Yeah, once you do that, you can express r as a smooth function of theta, right? And for applicable values of theta, let me mention that where theta is satisfies this particular inequality. On the other hand, I can use Kepler's second law, r squared d theta dt is the magnitude of the angular momentum. In order to show that t is, I can basically integrate it in order to show that t is a smooth function of theta, and it's smooth with a non-vanishing derivative. And there's an amazing theorem. It's a very beautiful theorem in multivariable calculus. That's the inverse function theorem. And that says if you can do this, then you can at least locally express theta as a function of time. You can invert this problem in order to express theta as a function of time. And as someone mentioned that you can actually figure all of this out using the Laplace Rungelin's vector. You can actually Hart-Goldstein's group has the entire proof of what the actual formulas for theta and r will be. And if you do that, you actually find out that these theta and r satisfy the Newton's equation. And essentially, once you express theta as a function of time, then you can express r as a function of time, and therefore you can express x as a function of time. So, once you have a given velocity circle, you can actually figure out. So, once I prescribe the velocity in a certain manner with some certain radius and with some certain radius and a fixed constant, and some certain center, then work back to the I can actually work back to um, the defining the equation of an orbit. And so let me go ahead. And the particular case that I'll be talking about is actually the case where you have ellipses in the Kepler problem. And if you have 0 less than epsilon less than 1, you have an ellipse with the focus at the origin, and with the minor axis being minus k by e and the with the major axis being minus k by e and the minor axis being norm of h squared by k. I think there will be a factor of 2 over here that's kind of missing. There should be a 2 over here, I suppose. Yeah, I think there's a 2 over here. With a yeah, there will be a 2 over here. With the and the minor axis being norm of h squared by k times 1 minus epsilon squared. Twice that actually.
That is
At
true
any
here.
sorry, the k is the one the constant in the equation.
Okay, that momentum.
So k no. K is this equation, this term.
Okay, it's GM naught you are saying.
Yeah. So let me go ahead. So the reason I'll be interested in ellipses is because when we study geometries, we'll actually go to the idea of we'll actually study the regularization of the Kepler problem for negative energies. And in those cases you have ellipses. You can do a similar procedure for zero energy or positive energy, but it just turns out that negative energy is easier to explain. Okay, am I audible? Am I audible still?
Yes,
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 yes, you're audible.
Great. Um, right. Uh, Moving on, let me mention a little lemma, and this lemma is again essentially due to the Greeks. That if you take a velocity circle and you take 2 points that lie on a common line through the origin, then v1 dot v2 is norm of c square minus r square, and this you can actually show that this is 2e, twice the energy, where r is k over norm of h. And the outline of the proof is first you show this, and this requires yeah.
Yeah, sorry, can you go back one slide?
Yeah, sure.
Yeah. Means you are saying that V1 and V2 are diametrically opposite.
No. I have not mentioned that V1 and V2 are diametrically opposite. I'm saying that there's a common line through the from the origin, or like common lines through the origin on which V1 and V2 lies. So here's a diagram if you're interested.
Okay.
Here I have the origin. I take a line and I take
Mm-hmm.
2 points on the circle over which they intersect, on at which they intersect. So one of them is V1 and the other is V2. And this is not necessarily the diameter.
So what is the meaning of diametrical, like the 2 point opposite to the origin?
Sorry?
What was that the 2 points should be either side of this origin you were saying? We'll go back to the
No.
previous slide.
I'm saying that they lie on a common line through the origin. So, you have this circle over here, let's say, and you have let's say you fix an origin over here. And I can take multiple lines, right, to the origin that intersect the
Yeah.
circle at points. So these are my V1 and V2, where they intersect.
Okay, means
Does that make
there are
sense?
multiple lines. Okay.
Yeah, does that make sense?
Okay, yeah, let us see the proof then.
Right. And the proof is essentially a geometrical argument that you consider the point diametrically opposite to V1, and then you draw a right angle triangle, and then you can define a vector E to be V1 minus C, which is the radius vector pointing towards this direction from the center. And then you can express this diametrically opposite point to be C minus E. And then you can actually see that V1 dot V2 is the same as V1 dot W, because V2 minus W is perpendicular to the line connecting V1 and V2. And then you can yeah.
Actually, can you
What's that?
go on doing the proof, because speaking only is not helping.
Right. Fine. So I think you are. Is it clear that the quantities I've defined E and W? Is it clear geometrically the quantities?
W, I think it's a point on the circle, and what is vector E, which is
Vector. So you have this circle, right?
yeah.
And you have the origin over here. You have V1, V2. This is the vector. These are the vectors. And you have the center over here. You take the point diametrically opposite to V1. You name it W. And then this is the center. And then you can actually figure this out that uh, this vector is basically, if I call this vector as C minus V1, I call this as C minus V1 and I name, this is the vector C minus V1. I call this as E. And then you can actually figure this out that W is C minus E. It's easy to see that. I'm not going to prove this. And then let's complete this triangle. And then this is V2 minus W. And then and you can see that this is a diameter and this is a triangle with triangle on a circle with one side as the diameter. So this must be a right angle. This is standard Euclidean geometry. And then you have V1 dot V2. And I can write this as V1 dot V2 minus W minus V2, right? And let's see. Yeah, and I can write this in this form because V1 is perpendicular to W minus V2, right? V1 is perpendicular to V2 minus W. So in essence, it's perpendicular to W minus V2, right? And then I have this as let's put it as V2 minus W. V2 minus W. Yeah, this makes a lot more sense. I can write this in this way, and then this is essentially the same as V1 dot W, but then you can see that V1 dot W is norm of C square minus norm of E square, and norm of E square is nothing but the radius of the circle. So yeah, that's basically the proof of it. I'm not going to do all the computations individually. So I'm quite sure a lot of you will be familiar with the idea of stereographic projection in some form or other. But let me present you an outlook on stereographic projection that I learned from Milner's amazing paper, and this outlook has a lot to do with the Gratian idea of circle inversion. So what I'm going to call SNRP to be the sphere of so sorry, this will be of radius r, to be the sphere of radius r centered at P. And this is an n-dimensional sphere of radius r centered at P, and Sn is our unit sphere. Yeah, and what we'll do is let's briefly define the idea of inversion with respect to a sphere. So the idea is, let me show this diagrammatically. So the idea is, you have this sphere with some center at P, and what you do is you take any point in Rn, let's say some point x, and so you have, and you take a ray from P to x. So here's a ray from P to x. Then you consider this distance, r squared, where here's our radius r, by norm of x minus p. You consider this distance. So you walk this particular distance. Along the ray, and you end up at some point y, right? And this is what the process of inversion does. It takes x to the point y, and where y is defined in this particular way, that you consider the ray from P to x, and you take a particular distance of r squared by norm of x minus p along that ray. Okay, and if that is clear, let me also mention this real quick, that when I say that you consider this but a distance of r square by norm x minus p along that ray, what I mean is the distance of y from p is r square over norm x minus p. And you might write this as r by norm x minus p times r. And then if norm x minus p is r, so if p lies on the sphere, what you end up with is that y lies on the circle as well. And so basically, if if x lies on the sphere, then y and x are essentially the same point. On the other hand, if so x so x minus p, if x minus p is equal to r, then you have y is x, and then if x minus p is greater than r, if x minus p is greater than r, then this term becomes less than 1, and then y minus p is actually less than r. And in that case, what you end up with is that the point y lies inside the circle, inside the sphere. And if x minus p is less than r, then this particular term, r over norm x minus p, is greater than 1. So norm of y minus p is greater than r. So what inversion does is it takes the inside of the sphere to the outside and the outside of the sphere to the inside. And now note that this process is not well defined for x equal to p. So what I'm going to do is I'm actually going to formally attach a point to Rn plus 1, which I'm going to call infinity. And this point is thought to be the inverse of the point p. Now, if you're familiar with, to some degree, with compactification, what I'm essentially doing is I'm sort of compactifying Rn plus 1 with the sphere. That's essentially what I'm doing. I'm actually taking the sphere to a one-point compactification of Rn plus 1. But again, if you're not familiar with this, then you might actually think of it as somehow I'm assigning a formal point infinity to Rn plus 1, such that this point infinity is the image of the map P, image of the point P under the inversion map. And I'll mention a convention now. I've also included it later. And the convention is that this point infinity belongs to every straight line or hyperplane in Rn plus 1, but does not belong to any sphere. So this is a convention I want you to keep in mind. We'll use this later. And so here's, yeah.
So apart from infinity point, is this conversion like well defined and it works?
Yeah. This is well defined. This is well defined.
Okay.
Because you can see that the right hand side, so norm of y minus p is well defined for every x other than p. Right.
Yeah.
So what I can do is, so given an x and a p, I can write down an equation for a ray that starts at p and points in the direction of x. And if you do that, you walk on the ray until you reach a distance of r square by norm of x minus p. And that point, that's where you like put down your flag and say, this is where my point y is. Does that make sense?
And what is this r, our n plus 1? This is in the second point.
This is n plus 1 dimensional Euclidean space.
So you will map that, okay.
So we are actually mapping a map from. Yeah, I mean, when I'm considering spheres, I'm actually considering n spheres. N spheres in Rn plus 1. Yeah. And as you might know, n-dimensional spheres, or by definition, n-dimensional spheres live in Rn plus 1.
Yeah.
Right. And yeah. And so essentially, this is a mapping from Rn plus 1 to Rn plus 1. Right. And now, let me explain this figure a bit. Here we have a sphere the dotted lines represent a sphere with respect to which we are inverting, and it has some radius. Let's call this capital R, and this is centered at P0. Okay, so the dotted line sphere is centered at P0, and I consider a sphere of radius small r, which passes through the point P0. Is that fine? And then I consider a hyperplane uh, of dimension n minus 1. And then you can have the following construction. You can consider from P0, draw the normal to the hyperplane, and then you consider a point X on the sphere of radius small r. Again, I am not taking any assumptions over here that small r is greater than capital R or small r is less than capital R or any of those assumptions. The only assumption in this is that the sphere of radius small r passes to the point P0, which is the center of the sphere of radius capital R. Having said that, let's take a point X on the sphere, on the smaller, quote unquote, smaller sphere. And if you draw a line, that passes through X and meets the hyperplane at a point Y. And then you notice that this triangle, and the outer triangle are actually similar triangles. And from what you might have studied in geometry is that if I have similar triangles, I can actually consider ratios of corresponding sides. And so if I consider this ratio, I can write y minus p0 is, I can express y minus p0 in this particular form. And then once I do this, if I choose R such that R square satisfies this particular criteria, then the sphere of radius small r, then this particular sphere maps to this particular plane under inversion. And that follows by definition, because if I put R squared to be this particular quantity, then over here you have y minus p0 is R squared over x minus p0. And then you can do a completely analogous procedure, or you can like think of it the other way around, where I actually, instead of starting with a hyperplane, I fix the radius of the sphere of inversion. So I fix small r, and then you can actually move your hyperplane around so that this particular sphere maps to a hyperplane. So it works both ways. So the essential point that I'm trying to make over here is that if any sphere passes through the center of the sphere of inversion, then it gets mapped to a hyperplane of the same dimension. And this, I have mentioned this argument for spheres of dimension n-1, but this works for any dimensional spheres. So it works for any K spheres, and you can generalize this for any K sphere. So
what was the role of that dotted sphere?
So the dotted sphere is a sphere with respect to which you're inverting, with respect to which you're considering the inversion.
But you are mapping the points from the inner sphere to the plane.
Yeah. So what I'm doing is, let's make this a little bigger. So here is your dotted sphere, and you're inverting with respect to this sphere. Okay, and here is some other sphere which passes through the plane, which passes through the center of the dotted sphere. Okay, and the point I'm trying to make is that this inversion, if you appropriately select the radius of the dotted sphere, then this inversion is going to send this sphere to some hyperplane of the same dimension. So if this is, let's say, a K sphere, then you end up with a K hyperplane. Is that fine?
Still I'm not getting the idea. So in the previous slide, you defined that we can map any exterior point to the interior of a sphere by the formula. And I think I agree with this. But in the
Hmm.
second case, you are taking a sphere, the
Yeah, and I'm
points are
taking a second sphere. I'm taking a second sphere that I'm inverting. So this is a sphere. The dotted line represents the sphere with respect to which you're inverting. The second sphere
okay.
is a particular sphere that passes through the center of the sphere of inversion.
Okay. So if I
Is that
understand
fine?
correctly, it means that all the points on the inner sphere,
Yes.
you are mapping it to a hyperplane.
All the points in this particular sphere is
Yeah.
mapped to a hyperplane.
Okay.
Okay, and you can do this for any case sphere. So you might fix a sphere. So if I fix the sphere of inversion and I take any k sphere, then all points of the k sphere get matched to a k hyperplane, provided that the k sphere passes to the point p0. And I'm going to emphasize this point, that the k sphere has to pass through the point p0, and the p0 being the center of the sphere of inversion. Is that clear?
Okay. Let us see this thing. And r
Okay.
square, you are getting capital R square. That is the radius of the
Yeah, capital
dotted
R is the
sphere.
radius of yeah, capital R is the radius of the dotted sphere. And the proof is essentially using the definition of the inversion map, as well as using the definition of as well as using some concepts in basically what I would say middle school geometry, using the concept of similar triangles.
Mm-hmm.
Yeah, is that fine? Okay,
Yeah.
moving on.
One
So
more thing
now,
here.
yeah,
It is that it seems that I'm only one asking the question. So is this okay with like the students or this year?
it's fine. It's
Yes.
fine. Probably they don't have questions. It's fine. Let's not
Oh,
assume anything.
actually, some do. Just sorry, just 1 minute.
Yep. Hello?
Yes. So some of them do have questions. So I guess Akash had some questions. So would you like?
Yeah,
Actually, I was
yeah, I think
planning.
I think you can fire away. I think
Okay.
you can fire away if you have
Okay.
questions.
Actually, I was planning to have the question and sessions like right at the end. So okay. In
I mean,
that.
if you have questions that genuinely interrupt your flow of understanding, then you can ask them now. If you have any other kinds of questions, then we can keep that at the end of the talk. If you have a question that genuinely interrupts your flow of understanding, then you can ask them.
So the first is you can actually ask your questions now. If you have any trouble at understanding, feel free to ask.
Uh,
Hello.
Hello.
Yes,
Yeah.
go ahead.
I have a question that is it necessary to we have to place the angular momentum vector on z-axis?
No,
It
it's not necessary. It makes life easier. That's all.
so can you explain a bit more, please?
So, so let's say you have the x, y, and z axis, right? Here's your
Okay.
x, y, and z axis, right? And here's some angular momentum vector. So
Okay.
I can, in principle, rotate my x, y, and z axis so that the z axis points in the direction of the angular momentum vector. And the reason it makes life easier is that you just need to consider the x and y plane. You don't need to consider the plane z. You can do everything if you don't do this transformation, and everything works out fine, except that life is a bit more difficult in that case. Your computations are a bit more difficult.
Okay. Thank you.
Any other questions? Okay. Any other questions? I guess not. So, Otishmanda, I think you can carry ahead.
Sure. Carrying on. So as I mentioned, that any case sphere passing through P0 maps to a K hyperplane and vice versa. And then let me now define stereographic projection. And what stereographic projection? The way we define stereographic projection is the following. So let me just go back. Let me mention something real quick. So So if I have a sphere and a plane, I can actually define a one-to-one correspondence between them by choosing an appropriate sphere of inversion. Is that clear to everyone? If I take any sphere and any plane, I can actually find a one-to-one correspondence between them, provided that I choose an appropriate sphere of inversion. And then the stereographic projection is defined, or the standard stereographic projection is defined to be the one-to-one correspondence between the unit sphere and Rn via inversion with respect to the sphere of radius √2 centered at the point with all coordinates 0 except the last coordinate being 1. So let me briefly draw a diagram of what I'm trying to mention. So for the 2 sphere, here's your 2 sphere, and this is your coordinates 1, and this is the hyperplane R2, and then the sphere of inversion is a sphere of this particular form. This is a sphere with this point being the center. It's probably not evident from my diagram. Yeah, whatever. This point is the center, and this distance is √2. So you're inverting the unit sphere with respect to a sphere which is centered at the point at this particular point, let's say the north pole of the unit sphere, and the radius of the sphere of inversion being equal to √2. Having said that, so now if I consider great circles, so what are great circles? Let me just briefly mention what great circles are. So given a sphere, again sphere of any dimension, a great circle is a circle that that has the center as the center of the sphere and the radius to be the radius of the sphere, and it goes on the sphere. An example of a great circle would be the equator. Another example of great circles would be the longitudes on the sphere. So if I have a great circle passing through the pole, then actually, by what we discussed, these map to straight lines passing through the origin in Rn. And yeah. On the other hand, you can define the standard way to define the stereographic projection, and it turns out to be the same thing if you use the way we have defined, is to consider the map from Sn to Rn that sends a vector u1 to un plus 1 to the point u1 to un by 1 minus un plus 1 in Rn. So this is in Rn. And you can work this out. You can actually work this out, and I'm not going to do this, despite what Krishna says. You can work this out that on the sphere, if I take, so I have some point u, I take the diametrically opposite point, and this diametrically opposite point is minus u. So if I send the point u to minus u, then the image of f goes to the point minus v by, so if v is the image of f, then this maps to minus v by norm of v squared. And what this means is, if I consider two diametrically opposite points, then these correspond to points v1 and v2 in R3. And as I mentioned that, so these correspond to points v1 and v2 in R3. And these points lie on a common line through the origin and satisfy this particular criteria. The reason these lie on a common line through the origin is if v1 is, let's say, v, and v2 is minus v by norm of v squared, then V2 can be expressed in the form lambda V, with lambda equal to -1 by norm of V squared. And this is an equation, and sorry, lambda V1. And then and the equation of a line through the origin is nothing but uh, or the set of points that describe a line through the origin is nothing but lambda V, where lambda belongs to R. So V1 and V2 lie on a common line through the origin, and these satisfy this particular criteria that V1 dot V2 is equal to -1. Now, let me go back a second and show you something that might be familiar. So you have this particular criteria V1 dot V2 equal to -1, and V1, V2 lie on a common line to the origin. Let me go back to this lemma, which says that for a velocity circle, if I take two points that lie in a common line to the origin, then this satisfies V1 dot V2 is -2e. So in this case, if I have e to be -half, then you note that V1 dot V2 is equal to -1. So I can interpret a velocity circle as coming from a stereographic projection. And but before I jump to conclusions, let me mention this, that there's a lemma due to Steiner, and this is in the year 1826. Steiner was one of the first people to actually extensively study inversive geometry. And the lemma states that the operation of inversion is conformal. By conformal, I mean that if I take, let's say, two lines passing through, or two circles that intersect at a particular angle, then their images are intersect at the same angle. So the operation of inversion is conformal and carries every k-sphere or k-plane to a k-sphere or a k-plane. And so if what this means is, or you can actually explicitly show this, that if you do not have a sphere that passes through the poles, if you do not have a sphere that passes through the center of the sphere of inversion, then that maps to a sphere that does not map to a plane. And similarly, if you do not have a plane that passes to the center of inversion, then this actually maps to a plane. So the great circles that do not pass through the poles map to circles in Rn that satisfy the criteria V1 dot V2 is -1 whenever V1 and V2 are on a common line passing to the origin. And all of this can be inverted. So if I prescribe such a circle that satisfies this criteria, then I can get a great circle on the sphere. Is this clear?
Yes, I just had one question for myself,
Sure.
that the dot product of V1 and V2, since it can, since you have taken it as -1, uh,
Mhm.
and like previously you stated that V1 dot V2 equals 2e. So is the value of the e, is it restricted anyhow?
Yes. So actually, if you consider, so we'll shift now from this picture and use it to the velocity circles. And for the velocity circles, we'll prescribe that e is -half.
Okay, so we can, so e, is it just -half, or is there any range, or
No, no, no. It's just -half, so that you get V1 dot V2 is -1. Um,
okay?
I should mention this, that the regularization procedure will be carried out for e equals -half, but it can be extended to any value, any negative value of energy, by changing the radius of the sphere. By changing the radius of, instead of considering Sn or a unit sphere, you consider a radius of sphere that's equals 1 over you basically scale the radius to a particular value. I don't exactly remember the value to which you scale, but you can essentially do it for any energy by scaling the radius of the unit sphere.
Okay. And
Okay.
just for a little bit of visualization, can you just give a brief idea of what a k-dimensional sphere or a plane might look like, or how we should imagine of sorts?
Uh, 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 so for example, a one sphere would be a circle, a two sphere would be the usual sphere, and from three spheres I can't explain. It's just explained from the point of view of an equation,
Okay, understood. Hmm.
right?
So I would like
Uh,
to add here something.
yeah.
So the like in physics, how we study n-dimensional sphere or something is like for three dimension we have x square plus y square plus z square is some constant value, where x, y, z are the points on the sphere with respect to origin. So for n dimensional sphere, that 3 will be n, like x1 square plus x2 square,
N plus
therefore
one.
go on. Yeah. So it's just a mathematical construct and nothing else.
Yeah.
And
Krishna, I should hurry a
just,
bit now.
yeah, yeah, so
So moving ahead. So now let me essentially come to the problem of regularization. And to come to the problem of regularization, I need to go way back to the equation x double dot plus kx by x cube is 0. Um, Point is, these equations do not hold at x equal to 0, right? These equations are not defined for x equal to 0. And the idea is, we would like to, and so let's note something, that if x equal to 0, then the angular momentum vector is actually 0. And so what we want to do is we want to study how our orbits will be if there is if the angular momentum vector is 0. But unfortunately, you can't do that from the equation. You can't do that from the equation precisely because the equations are not defined at x equal to 0. So we need to somehow extend, or we need to somehow come to a picture which allows us to interpret singular orbits in a way that is quote unquote natural to an extent. So having said that, let me also mention that if the angular momentum vector is 0, the velocity circle actually blows up to infinity because there's h in the denominator. So um, so as for example, if I take h goes to 0, the radius of the velocity circle keeps blowing up until it blows out to infinity. And so you're in some kind of a trouble. And so we would like to have a picture where we can understand that where we can have an interpretation of orbits for which angular momentum is 0. And in order to do that, what we will do is, yeah, in order to do that, we will use stereographic projection. So what we'll do is we'll first stereographically project S3 to R3. And here R3 I'm considering to be my velocity space. And then, as I mentioned before, if you have a great circle which does not pass through the poles, then these circles under stereographic projection yield velocity circles that satisfy. So these velocity circles satisfy v1 dot v2 is -1. And so this is nothing but minus 2 times, sorry, 2 times, oops. Yeah, this is nothing but 2 times minus half. So the great circles which do not pass through the poles map down to velocity circles with an energy of minus half, or corresponding to orbits of energy minus half. And so that is fine. There's no trouble over here. On the other hand, we might ask, we know that if there's a great circle passing through the pole, it has to map down to straight lines in the velocity space. So let me draw this thing a bit, what I mean. That helps. You have, this is your sphere S3, and this is your R3, let's say. And so if you have so this is the pole. So if you have a great circle that does not pass through the pole, then this maps down to a great circle that to some velocity circle in R3. And this is fine and dandy. On the other hand, if you have a great circle that passes through the poles, these actually maps to a straight lines passing to the origin, as we mentioned before. And so we might ask that what do these straight lines in velocity space represent? And to understand this, let me mention that as the angular momentum goes to zero, the semi-major axis, the semi-minor axis of the ellipse goes to zero. So the ellipse actually flattens to a line segment. And here we'll use a convention. And the convention is that if the angular momentum is zero, so as I mentioned, the ellipse flattens to a line segment. So you have some kind of a line segment over here. And the convention is that if you have zero angular momentum and your xt falls freely towards the origin along this straight line, then I'm going to assume that it gets reflected along the same straight line when it hits the origin. So it goes here, and then there's the bounce, and then it goes back. And so this is actually physically corresponds to, if I have a mass m and a small mass m, this actually corresponds to an elastic bounce. And then, as I mentioned, another convention that the point of at infinity belongs to every k-plane, but does not belong to any circle. And so what you can do is, if you rotate this, if you rotate the axis, you can put the orbit in the form that t goes to rt00, where basically I am saying that this particular straight line is oriented along the x-axis. So now, if I take this and RT has to satisfy this particular differential equation, which you actually get by conservation of energy. And then you notice that the velocity map is nothing but t goes to dr dt 00. So if I do that, then the velocity is entirely constrained along the x-axis. So the velocity gets entirely constrained on the x-axis. So the velocity lies on a straight line. And as r goes to 0, then first as r goes to 0, the velocity starts decreasing to minus infinity. Then you have the bounce, and then the velocity vector sort of sweeps through the point at infinity and then goes back to 0. Right? Does that make sense? So here's my point 0. So as r goes to 0, you're approaching. So the velocity keeps increasing in magnitude. But since you're approaching, the velocity actually increases towards minus infinity. And then when it does, and when you end up with the elastic bounce, it actually sweeps to the point at infinity and then turns around since this the particle turns around after the elastic bounce. So it sweeps to the point at infinity, then it turns around, and then it goes back to 0. Again, mathematically, what I'm doing is I'm considering a one-point compactification of R. So this is equivalent to considering a stereographic projection to a circle, where you are kind of basically, yeah, this the north pole of the circle corresponds to the point at infinity, and this point corresponds to 0. And then this is a one-point. So basically, what I'm doing is I'm considering a one-point compactification of the circle. Yeah. So you start at somewhere over. Just You should have your zero somewhere over here, let's say, and then basically what you're doing is uh, oh no, no. Your point at infinity is here, and your zero is on the other side. So you go all the way up to infinity, you cross it, and then get back all the way down to zero. So if you're familiar with one-point compactifications, this is what I'm doing. If you're not familiar with one-point compactifications, you can interpret it this way, that as you reach the origin, as x approaches the origin, your velocity increases. But since it's approaching, the velocity increases in the opposite direction, increases towards minus infinity. Then when you hit the origin, the velocity has infinite magnitude. And then when you get away from the origin, your velocity has actually positive magnitude, because you're getting away from the origin. And yeah, so the velocity vector moves in a straight line, and it sweeps to the point at infinity. And in our picture, these velocity vectors then essentially become the straight lines that we wanted to talk about. So if you have any straight line in the velocity space, this actually corresponds to singular orbits. And then I can actually use the inverse stereographic projection to map these back to great circles passing through the poles. And why this regularizes the problem is because I can consider any great circle on the pole, on the sphere, on S3, and that can be any particular great circle that may or may not pass through the poles, right? And I can actually continuously move on the great circle without any kind of singularity, right? But these great circles are nothing but something that arises from the velocities, from the velocity vectors in a perfectly analytic way, so as to say. And so yeah, this is how we end up regularizing the problem. And there's this amazing theorem that says that if you have a velocity vector, then or if I consider the velocity space, and I am also considering the point at infinity, then if I consider any curve in this velocity space, so I have this velocity space M, and I have some curve, let's call this gamma, and I consider walking on this curve to some, or let's say I want to find out the length of this curve gamma. So if I want to find out the length of this curve gamma, then I can actually calculate this integral over gamma of dt over mod of xt. And then what is, and if you have such a prescription of length of a curve in M, then you find that M is isometric to S3. What I mean by isometric is that lengths in M are the same as the lengths in S3. Right. So that's the geometrical side of understanding regularization. Let me briefly mention an analytical side, which comes from taking central force motion in the complex plane. And the reason you can do this is because central force motion is essentially planar, because angular momentum is conserved. And as I mentioned, if you conserve angular momentum, you can represent the whole motion in the xy plane. So I take any xy in R2 and I consider the corresponding complex number. And then you can calculate that the gradient of a function, any function uxy, goes to basically twice del del z bar of uz z bar. And then you can consider any central force motion and represent it in the complex plane. And if you do that, you can also show from here that energy is conserved in the complex plane as well. And what we'll do is so the first procedure we have, or the first step in this procedure, is you assume that z is some analytic function of w, and you take this equation and you plug everything back in, and you end up with a ridiculously complicated equation. And then what you do is you do something that's called a time transformation. This is called a time transformation. And the parameter S is often called a fictitious time parameter. So you do a time transformation, and I'm just assuming G is analytic. I haven't prescribed anything for G. Uh, uh, and then you plug everything back in, and you end up with an expression that is even more ridiculous. And then you plug everything in the energy conservation equation, and then you get one more equation that is of this particular form. And if you figure out what w prime squared is from this equation and plug it back in over here and wherever you find a w prime squared, and then you'll need to take some terms common, some terms as separately, and you'll find that a lot of stuff gets cancelled. And you take, all right, and you prescribe that GW, which I hadn't prescribed till now, is F1 of W. So if I plug this over here, you can see that this W prime terms get cancelled. So this goes to 0. And then everything can be clubbed out neatly into a central force motion. Into a motion that is, into a central force motion with a potential of, with a potential that can be written as F1 with a potential of this particular form. But the crux of all of this is that if I start out with a central force motion, then I have a corresponding central force motion that occurs in a fictitious time. And if that's the case, I can do the exact same thing for the Kepler problem, or for any power law potential for that matter. And if I do this for any power law potential, you actually end up with the fact that the Kepler problem maps to the harmonic oscillator problem, and vice versa. The harmonic oscillator problem maps to the Kepler problem. And why this is important is that in complex coordinates, the Kepler problem has this particular form. And the harmonic oscillator problem has this form. And you notice that if you do this, so what I'm saying is, if you do this transformation, then you get to a harmonic oscillator problem in W in a fictitious time. So you have W primes over here. And let's say I call this K tilde to be 0. And if you do this, you notice that the harmonic oscillator problem does not have a singularity. The Kepler problem has a singularity. The harmonic oscillator problem does not have a singularity. And so this complexification of central force motion essentially yields that the Kepler problem and the harmonic oscillator problem are duals of each other. And since they're duals, you end up regularizing the Kepler problem because the harmonic oscillator problem does not have a singularity. And I did not mention this, but this is dual in a much greater sense than merely the fact that the Kepler problem and the harmonic oscillator problem map to each other. It's dual also in the sense that the energy of the Kepler problem is the energy of the Kepler problem transforms to the energy of the harmonic oscillator problem, and the angular momentum of the Kepler problem transfers to the angular momentum of the harmonic oscillator problem. And for those who are familiar with the Laplace-Runge-Lenz vector, the Laplace-Runge-Lenz vector of the Kepler problem transforms to the Yauch-Fradkin tensor of the harmonic oscillator problem. So there's a regularization side of things why this is important. There's another side why this is important. Yeah, I think you have a question, Krishna.
Yeah, I'm surprised that you are mapping a 1 by
Sorry?
cube. You are mapping a 1 by cube potential to a linear potential.
Sorry?
Like I am wondering that you are mapping a 1 by cube potential, a power law potential, to a linear potential.
Yes, 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 yes. It's a one by not a one by q potential. It's a one by x potential, one by r potential, two and r square potential.
Yeah, but by R potential. Yes. So this is true only for that 1 by R
No, no,
potential, or it
no, 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 no. This is true for every power law potential. Every power law potential has a dual potential, and that duality is expressed by that this fact that if you have a power law potential of the form something like a mod z the power nu, then you end up with a dual potential of a tilde mod w to the power mu, where mu has this particular form. And in case of power law potentials, these are dual. But in case of any general central force motion, you will get something in complex plane that is also central force motion that may not be dual in the general case. Over here, if you start with a mu of this form, you get back a nu. You
so
get back the same nu.
the only thing which is going to vary is that value of the spin constant, the k prime value.
Sorry, sorry. Your voice is breaking up a bit.
So the only thing which is going to vary is the value of the spin constant, that is k prime.
Yeah, yeah. The value of the spring constant will vary, but the energy of so in the case of the Kepler problem and the Hooke problem, the energy of the Kepler problem maps to the energy of the Hooke problem. The angular momentum of the Kepler problem maps to the angular momentum of the Hooke problem, and the Laplace-Rungelen's vector maps to the Young-Fredkin tensor. And this is a very, very crucial
Yeah,
fact.
yeah, that is what I am also wondering. Like, you know everything about harmonic oscillator.
So, are you asking that whether this mapping is only specific to the harmonic oscillator and the Kepler problem for energy and angular momentum? Is it only specific to the harmonic oscillator and the Kepler problem? Is that your
Yeah,
question?
if you can mention that one, that would also be
Yeah, I mean the energy and the angular momentum is specific to the mapping of conserved quantities is specific for the harmonic oscillator and the Kepler problem. But the duality is holds for any kind of central force motion or any kind of power law potential. Does that make sense?
yeah, makes sense.
So what I'm saying is, if you start with any power law potential, a mod z the power nu, you get a power law potential of a tilde mod w the power mu, such that if you start with a power law potential, if you start with this potential now, and you invert the whole procedure, then you get this procedure, or I mean, instead of, I don't mean invert the whole procedure, sorry. If you start with this potential and you repeat the same procedure, you get a mod z the power nu. And the mapping of conserved quantities is specific to the harmonic oscillator and the Kepler problem. And let me also mention something really interesting in this case. The Kepler problem and the Hooke problem are the only two central force motions that possess additional conserved quantities than energy and angular momentum. It is remarkable that that this additional conserved quantity. So for the Kepler problem, it's the Laplace-Rungelen's vector. For the Hooke problem, it's the Young-Fredkin tensor. It's remarkable that this process maps the Laplace-Rungelen's vector to the Young-Fredkin tensor. And also, the Kepler problem and the Hooke problem are the only two central force motion that possesses stable closed orbits. And it's also remarkable that these two map to each other. Uh, yeah. Having said that, let me. Yeah.
Are you going to discuss about those two additional conserved quantity some time in your class?
No, I am not going to discuss about Laplace-Rungelen's vector or Young-Fredkin tensor. I'll mention some of the references where you can find them, but again, I don't want to. I don't want to bring up additional things that to overcomplicate things, but this is I'm mentioning this uh, because maybe some of the people over here might want to read all of this up later. So that's why I just wanted to briefly mention this without going into too much details. Right. And let me conclude with a brief epilogue that you can do this process in quaternions as well. One sec. Yeah, you can do this process. So we did it in complex numbers, and you can do this process in quaternions as well. So what are quaternions? Quaternions are so to people familiar with division algebras, these are the division algebra of dimension 4. To those not familiar with division algebras, you might think of this as an extension of complex numbers. So in complex numbers, you have this thing that I square is -1. In a quaternion, you write a quaternion Q. Let me put a vector to be of something that has Q0 plus U1, Q1 plus E2, Q2 plus E3, Q3, where EI squared is -1 and EIEJ is this Levi-Civita tensor times EK. And for epsilon IJK, you have this is 0 if I equal to J, or if two quantities are equal, if two indices are equal, and then you have this cyclic permutation of IJKs. If you have any cyclic permutation, you have epsilon IJK is 1. And if you do not have a cyclic permutation, you have epsilon IJK is 0 if, IJK is the cyclic permutation from 1 to 3. Yeah. So if you have a cyclic permutation from 1 to 3, you have epsilon IJK is 1. If you do not have a cyclic permutation, then if there is no cyclic permutation, is -1 if there is no cyclic permutation, and it's 0 if two indices are equal. And you can actually figure out the rules of multiplication for the quaternions. And the special thing about quaternions is that, or the special thing about division algebras is that you can quote unquote divide two things. So for people who are familiar with the language of group theory and vector spaces, a division algebra is essentially a vector space equipped with an operation on the equipped with a binary operation on the vector space that makes the vector space into a group. And that binary operation is separate from the addition operation. Now, so over here, I'll briefly go through this procedure. You have for every quaternion in X, you define a quaternion X star that basically changes the sign of the last coordinate. And then what you can do is you can take a map from the quaternions to R3, which takes X to X times X star. And then you impose a condition on this, because this is a map from a 4-dimensional space to 3-dimensional space. You have an extra degree of freedom. To make use of the degree of freedom, you can actually impose this condition. And this is actually a bilinear condition. You can check that you can actually impose this condition. And then you can take a time transformation, as we did that, as we took a time transformation in case of complexification. And once you take this time transformation, you can show that in this starred space, the Kepler problem leads to a harmonic oscillator problem in quaternions. And one thing that you can work out is that this problem is, in case of quaternions, this is not a dual problem. So if you start with a harmonic oscillator problem, you don't get a Kepler problem back. Now, to tie up both these things, a geometrical and an analytical approach, let me mention that you have this time transformation 1 over mod x. And this is remarkably similar to the way we define the curve, to the way we define the length of a curve. So if this integral is called S, then you might notice that ds dt is 1 over mod x. So you might think that this geometrical way of regularizing and the analytical way of regularizing, let's say using quaternary, are related at some level. And it turns out that they are related at a particular level. But I am not going to describe that because that is to an extent that requires a lot of preliminary material to explain. And let me briefly talk about the references. There is an unnamed reference that I have not included because formally I can't include this reference, and that is Wikipedia. Um, the other references are Goldstein's book, which is an amazing book if you want to have an introduction to classical mechanics. And if you want to study about stuff like the Kepler problem and how to calculate, how to find out the orbits and how to find out the motion in time, you should look in Goldstein's book, and as well as stuff about the Laplace congruence vector. Um, John Milner's paper on the geometry of the Kepler problem is the paper that got me interested in this field. And this essentially talks about the entire geometrical approach to regularization that I talked to you about. And it also includes the cases where you have zero energy and positive energies. So in case of the zero energy, you find that it maps to the plane. And in case of positive energy, it maps to the hyperbolic plane. And actually, if you look into John Milner's paper, there's a very good introduction to hyperbolic plane using inversion. Grandatti's paper talks about the entire complexification procedure, again in much more detail than I have mentioned. And it talks about the process, it talks about all of these dualities that I talked about, that the energy of the Kepler problem goes to the energy of the harmonic oscillator problem and so on. And Waldvogel's paper is based on a regularization using quaternions. And this process of regularization using quaternions is also known in the literature as Kustanheimer-Stiefel transformation. But if you look into the original Kustanheimer-Stiefel transformation, it's much more complicated than the way Waldvogel presents it. Right. And I guess that is it from my side. So if you have any questions, you can fire it.
Okay, so does anyone have any questions?
Yeah, I have a doubt.
Sure.
Yeah. So like if you would see the Kepler problem, the Hamiltonian of it is similar to that of the hydrogen atom problem. So only difference is this has been dealt in classical dynamics and that has been done in quantum mechanics. So the
Yes, yes.
same stereographic projections and all that, like will the same proof be applicable over there also?
There is, in fact, in quantum mechanics. So there is a regularization called Ligenschaft regularization, that they have applied this same idea in case of quantum mechanics. In fact, and it turns out that the same idea is similar to the idea of regularizing geometrically using S3.
Okay. Why? Because even I am working on the same problem on the geometrization of the Kepler problem, but with a different attitude. Like I'm using the symplectic manifolds and all that. Uh,
Right. I see. Yeah.
yeah. So
I
there,
could do symplectic manifolds, but then this is an undergrad talk mostly, so I didn't think of introducing that.
because there we have a correspondence like Poisson bracket to
Yeah,
commutator,
yeah,
so
yeah,
we can
yeah,
keep
yeah,
it
yeah.
like both aside. And one more
Yeah, yeah.
doubt is, yeah. So basically in Kepler problem, the next approach is like we'll deal the stability, like we usually calculate the stability. So using the regularization approach, can we find the stabilization of the Kepler
No,
problem?
no. The regularization has nothing to do with stability. The stability of Kepler problem, or in general cases, n-body systems comes from K, Kolmogorov-Arnold-Moser theorem.
Okay.
Yeah. So if you're familiar with if you're familiar with symplectic geometry to an extent, you might have heard that I can always convert my phase space to a torus, right, using action
Yeah.
angle variables.
Yeah. Actually,
Right.
I'm very. Yep.
Yeah. So the KM statement tells you that so for the n-body problem, the phase space actually foliates the torus. So you have different you have different. So if you're familiar with irrational lines on the torus,
Yeah.
then you know that there are dense irrational lines on the torus, right?
Yes.
So the KN tells you that for every frequency of the Kepler problem,
Yeah.
you have it's a statement on quasi-periodic orbits. So depending on the frequency, you have some dense lines on the torus, and then if you have some kind of a perturbation, then this most of these are only slightly perturbed.
Okay.
The essential system remains the same, except at perturbations at very small levels.
Okay.
Yeah,
Yes.
you might
So,
read through the actual KM thing. What I'm telling you is a very oversimplified idea, sort of. I would suggest that you read the actual KM thing.
no, actually, I know only till moment map, so I have to yeah, do the other stuff.
If you're familiar with moment maps, one thing you might decide to look at is the idea of the fact that the geometrical approach to regularization is essentially the same as using quaternions. There's a paper
Okay.
on that.
Okay.
Yeah, yeah,
Yeah.
you might look into that.
Yeah. Thank you.